Huge thanks to Thunderbird Perch for making this video possible. Thanks for watching. Please subscribe, like, and share. Think about it. A new world awaits. What if physics broke? Imagine waking up one morning to find that gravity has weakened slightly, or that the charge of an electron has drifted. This sounds like something from a science fiction story, a plot device to create a dramatic crisis. Yet, this is a question that physicists are seriously considering, though perhaps in a less dramatic way. We ask this question not because we think physics is wrong, but because we know our current understanding is incomplete. The theories we use to describe the universe work incredibly well up to a point. They are like a beautifully drawn map that has large, unexplored territories marked with "Here be dragons." This map is called the Standard Model of particle physics. It is one of the most successful scientific theories ever created, a triumph of human intellect. It describes the fundamental particles that make up all the matter we can see and touch, and it explains 3 of the 4 fundamental forces that govern their interactions. For decades, its predictions have been confirmed by experiments with stunning accuracy. But great success does not mean it is the final word. The Standard Model has profound limitations, deep cracks in its foundation. The Standard Model of particle physics is the rulebook for the subatomic world. Think of it as a list of ingredients and a set of instructions for how they combine. The ingredients are the fundamental particles, the smallest indivisible bits of reality we know. These include quarks, protons, neutrons, leptons, electron. It also includes force-carrying particles, photon, which carries the electromagnetic force. This model explains, with remarkable precision, how these particles interact through 3 fundamental forces. Electromagnetism, strong nuclear force, weak nuclear force. It's a rigid mathematical framework that makes specific, testable predictions. For example, it predicted the W boson-Z boson-Higgs boson. The first and most famous mystery that the Standard Model fails to address is dark matter. Our understanding of gravity, laid down by Newton and refined by Einstein, tells us how objects should move based on the mass they contain. When we look at a spiral galaxy, we can measure how fast its stars are orbiting the galactic center. We can also add up all the visible matter, the star's gas dust, to calculate how much gravitational pull there should be. The problem is, the numbers do not match. Stars on the outer edges are moving far too quickly, as if held in their orbits by a huge invisible mass. This discrepancy is enormous. Galaxies should have flown apart billions of years ago, but they remain stable. To explain that stability, we need about 5 times more mass than visible. We call this missing substance dark matter because it does not emit, reflect, or absorb light. If dark matter is a mysterious something, our next puzzle is a mysterious nothing that is pushing the universe apart. For most of the 20th century, physicists debated the ultimate fate of the cosmos. Gravity, the great cosmic contractor, pulls everything together. The expansion of the universe that began with the Big Bang works against it. Which force would win? In the late 1990s, astronomers studying distant supernovae made a shocking discovery. They found the expansion is not slowing down. It is accelerating. Something is counteracting gravity, pushing galaxies apart faster and faster. This unknown influence was named dark energy. Measurements say it makes up about 68% of the universe's energy density. It's the dominant component, and yet we have no idea what it is. The Standard Model has nothing to say about this force. The simplest idea is a cosmological constant, energy of empty space. Einstein proposed this to make a static universe, later calling it his biggest blunder. Now he may have been right for the wrong reason. When we calculate vacuum energy from quantum physics, the result is outrageously wrong. The theoretical prediction is about 10 circumflex 120 times larger than observed. This is the worst prediction in physics history. It shows we're missing something fundamental between gravity and quantum theory. Beyond the twin behemoths of dark matter and dark energy, the Standard Model has other, more subtle cracks. One of the most glaring is its complete omission of gravity. The model masterfully unites the electromagnetic weak-strong forces into a single quantum framework, but gravity stands apart. Our best theory of gravity is Einstein's general relativity, which describes gravity as the curvature of spacetime caused by mass and energy. This is a beautiful, classical theory that works perfectly on the scale of planets and galaxies. However, it is fundamentally incompatible with the quantum rules that govern the subatomic world. Bringing gravity into the quantum fold is arguably the biggest challenge in theoretical physics today. A theory of quantum gravity is needed to describe what happens in extreme environments like the center of a black hole or the first moments of the Big Bang, where immense gravity meets tiny scales. Without it, our understanding of the universe's origin and its most dramatic objects is fundamentally incomplete. The Standard Model simply ignores gravity, which is a fine approximation for particle accelerator experiments, but it means the model can never be a true theory of everything. Another puzzle that emerged to challenge the Standard Model involves neutrinos. These are ghostly particles that are produced in nuclear reactions, such as those in the sun's core. For a long time, the Standard Model claimed that neutrinos were massless. Faced with these profound mysteries, physicists are exploring many possibilities. Most involve adding new particles, new symmetries. But some consider a more radical, unsettling idea. What if the laws of physics are not fixed? What if the fundamental rules can change over time or vary from place to place? This is a deeply uncomfortable thought. Science assumes laws are constant and universal. An experiment in Geneva today should match one tomorrow or one on the other side of the galaxy. Laws mean two things: mathematical equations and the fundamental constants plugged into them. Examples: the speed of light, the gravitational constant, the fine structure constant, which sets the strength of electromagnetism. We call them constants because we assume they're the same everywhere and for all time. But what if that assumption is wrong? If we entertain the idea that physical laws are not immutable, how might such a change occur? There are several plausible scenarios that physicists are considering. The first is a slow, gradual evolution over cosmic time. Just as the universe itself is expanding and cooling, perhaps some of the fundamental constants are also slowly drifting. For example, the fine structure constant, which governs light-matter interactions, could have been slightly different in the early universe, billions of years ago. This drift would likely be incredibly slow, far too small to notice day to day. But it might be detectable over the vast timescales of cosmic history. A second possibility is environment dependence. The laws of physics depend on local conditions. Perhaps constants aren't the same everywhere. In regions of extremely high density or strong gravitational fields, such as near a black hole or a neutron star, the rules might be different. For example, gravity's effective strength might change in very dense matter. Physics would then be local, not universal. The idea of changing physical laws is profound, but it is not just a philosophical debate. It is a testable scientific hypothesis. If the constants of nature have changed over time, they should have left behind observable evidence. One of the most powerful methods is to look at light from extremely distant objects. Light travels at a finite speed. A galaxy 10 billion light-years away shows us 10 billion years ago. This light is a time capsule carrying a snapshot of early universe physics. Astronomers analyze the spectrum of this ancient light, looking for the characteristic dark absorption lines from elements. The position of those lines depends on the fine structure constant. If alpha was different, quasar lines should be slightly shifted versus lab measurements. The possibility that the laws of physics are not fixed is a humbling one. It challenges our deepest assumptions and forces us to confront the limits of our knowledge. For now, the evidence overwhelmingly suggests that the constants are, in fact, constant. The rulebook seems to be the same wherever and whenever we have been able to look. But the fact that we are asking the question at all is a sign of a healthy and vibrant science. Pushing our theories to their breaking points and questioning their foundations is how progress is made. These are not minor issues. They tell us that our current picture of the universe is, at best, a rough sketch. A more complete theory is waiting to be discovered, and it may be stranger and more wonderful than we can currently imagine. Science is a journey, not a destination. Thanks for exploring the unknown with us. If this journey moved you, like, subscribe, share, drop your biggest question in the comments. To everyone expanding our cosmic map, researchers, teachers, viewers, thank you.